been very nice, just even in the one day I've been here. It's been a very nice environment, and it looks like it's going to be a lot of fun.
Can you just sit all right back there?
Oh, do I? Yeah, microphone. Let me use the microphone. We'll make it easier. Sorry. Okay. So anyways, thanks for the organizers for this wonderful conference. And I'm going to give a chalk talk. And for those few people in this audience who come from BU, then know my style, which is that if it fits on one sheet of paper, this is the lecture. So unfortunately, this lecture actually is both sides of the paper. So we'll see what happens. Also, if I'm writing too small, please tell me to shout. And I want to make an apology at the very beginning because this talk is going to be very different style than Royce's talk because I am going to have equations, but part of the reason I have this on chalk is so I won't go too fast. And this is also an extremely, I would say, blue-collar story because I want to take a specific paradigmatic example, the kinetics of aggregation, and I want to demonstrate to you how you write down the equations that describes the evolution of the cluster size distribution and how you solve them. So I hope at the end of this lecture you have at least some sense about how you might attack problems of this type. So what I mean by aggregation kinetics, I mean the following. I have a cluster of mass I and a cluster of mass j, and they come together at some rate, kij, which we will spend some time discussing. And at the end of the process, we have a larger cluster of mass I plus j. So this is the process that I'd like to understand. And if you want to have a sense of like what this describe, think about the setting of Jell-O or the aggregation of planetesimals to make planets. There's just a million applications of this process. Aggregation of blood to make scabs when you cut yourself. So I want to understand the basic dynamical quantity is what I'll call Ck of T. So this is going to be the concentration of clusters of mass K at time T. So this is the basic quantity that I'd like to understand. So the first way to, the simplest starting point is something known as the master equation. So you already heard a little bit about this from Royce in a sort of theoretical perspective or an abstract perspective, and now I want to show you the example of the master equations for this specific example of aggregation kinetics. So let me write them down and explain them, and then we're going to try and solve them. So the basic quantity is the concentration of clusters of mass K, and we want to ask how this changes with time. So I'll put a dot to denote time derivative. And so there are two terms that describe how the concentration of clusters of mass K can change. You can either create clusters of mass K by having clusters of mass I and J whose sum happens to add up to K, and you can create a cluster of mass K in this way. And there's a corresponding loss term, where a cluster of mass K interacts with something else and makes something even larger still. So let me now write down the equation, and then I'll explain all the terms. So there is 1/2 the summation I plus j equals k. So we're looking at all combinations of clusters of mass I and mass j that come together and make mass k. The rate at which they meet is an abstract quantity kij, which can be computed from first principles, but I won't worry about it for the moment. And then in a mean field approximation that I'll spend more time discussing in a moment, the rate at which clusters of mass I and mass j meet is proportional to the concentration of clusters of mass I and the concentration of clusters of mass j. So this is already a mean field approximation because I'm assuming that the probability that such clusters meet is proportional to the product of the densities, and this is an overall conversion rate that once they meet, that they actually react to produce a cluster of mass k. So this is the gain term, and then there's the corresponding loss term, which looks like this. Ck interacts with anybody else, so ki, k, ci. The summation I equals 1 to infinity. So this is a finite sum, this is an infinite sum. So those are the master equations of aggregation kinetics. So let me just make some points about this. First of all, this is a mean field description. I'm assuming that basically here, this is a two-body function, the probability that two particles meet. And I'm writing it as a product of single particle functions. There's also no spatial fluctuations here. There's just a concentration which doesn't depend on spatial coordinates. So those two things are basically the mean field assumption. This is also another important assumption here is that there's bimolecular reactions only. It takes two to tango. You don't need three. And this bimolecular assumption is actually not a very strong assumption because if you started with a dense system so that you had to worry about many body collisions at the beginning, as time evolves, there's fewer and fewer clusters because you have started with a large population of very tiny clusters. You end up with a few clusters of large size, and so if you aren't dilute at the very beginning, you're dilute later on. And so this bimolecular assumption is actually not a very tough assumption. Another one is that we're taking the limit n going to infinity. I'm assuming that there's no fluctuations, that there's a uniform concentration everywhere, no spatial fluctuations, and no discreteness fluctuations. So I'm assuming the thermodynamic limit. And I'm also assuming, and this is probably the most important one, or an important one, is that there's no shape degree of freedom. So I'm assuming that my clusters are little spherical droplets, and when two clusters meet, they make still a larger spherical droplet. So we don't have to worry about anything except the size of the cluster. So the index J here is referring to the cluster mass, and there's no other degree of freedom that describes the nature of the cluster itself. So those are the master equations. There's one point here which just requires maybe a little bit of thinking, which is a 1/2 here. Why is there a half here and there's no 1/2 here? And there's an issue about counting the number of pairs properly. And the point here is that if you look, for example, if we want to consider the growth of clusters of mass 17, so I could have a term, 17 is 10 plus 7. So I could have K 10, 7, but then there's a 7, 10. And so the 1/2 here is to account for the fact that there's two different ways that I and J can combine to make a K. Then the 1/2 also, but then the other thing is that if you have, for example, for C16, there's a K8, 8, 8, C8, C8. And the point here is that two clusters of 8 are destroyed when you make a 16mer, and so that 1/2 takes care of all of that. So I'm going a little bit quickly on this little point, but I just want to point it out and you can think about it on your own. Question?
Can you just clarify something really quick? Because at the beginning you said Kij can be computed from first principles if you wanted to. But is that on the assumption that it's already in the right configuration for a reaction to happen?
So the question was, tell me more about Kij, basically.
Yeah, basically.
Yeah, so, well, actually, in the fourth lecture I'm going to give today, not today, on Friday, we are going to learn how you actually calculate this microscopic reaction rate. So it's the flux of particles of type I, say, meeting of particles of type J. So in a reaction rate picture, you imagine taking J as like a fixed sphere, and then you look at the rate at which imers will come to the surface of the J. And so this can be calculated in first principles. And I'll show you how to do it.
But you assume there's no kind of shape fluctuations or anything?
Yeah, so this again, no shape fluctuation is really important. We're always assuming spherical symmetry, yes. Okay. So this is...
You also commented, so this is a nonlinear equation.
Correct.
Versus what Royce talked about, what he was writing down master equations that were linear and P.
Right.
So, can you comment on that?
Well...
Just different dynamics?
Yeah, I mean, the point here is that because it takes two to tango, you must have a nonlinear equation. But the thing is that these equations, there is like a large bag of tricks available to solve them. And so maybe I solve them, and then maybe you ask your question again half an hour from now if you feel like, I'm not this dichotomy between linear and nonlinear equations. Most of the interesting phenomena that we have in non-equilibrium statistical physics are nonlinear in nature because you usually have either interaction of multiple clusters in aggregation kinetics, or you have coarsening processes where there's interfaces interacting in a nonlinear fashion, or the Ising models of nonlinear interaction. Royce.
Yes, can I just comment for the purpose, which is that the equation I would write down is all the C's.
Yeah, that's what I
all the C's, and that is this is a little bit complicated.
So from this, you can derive a master equation of P of Ci.
Oh, okay. Yeah, so the thing is that this is assuming the thermodynamic limit. So I'm assuming that, like the most fundamental microscopic description system is I have 13 clusters of mass 1, 17 clusters of mass 2, 123 clusters of mass 3, and I write the probability distribution to have exactly that many clusters of that type. And the thing is that if in the thermodynamic limit, you don't have to worry about the full probability distribution because it's sharply peaked, that there's an average number of clusters of mass 1, an average number of clusters of mass 2, and this is the description in which I'm writing this equation.
I see. So it's like the moments, the equation from arising from the moments of the mass equation that we're
Yeah, exactly so. Okay. Let's now solve these equations just so we get some feeling of what's the physical content of this. So I'm going to talk about the case of the constant kernel. And for reasons that are sort of perverse but make a lot of sense after the fact, I'll choose the constant to be 2. So let's write down the equations and just see what comes out. So let's just take these equations for Kij equals 2 and just write them one by one. So C1 dot is equal to 1/2. Well, 1/2 and 2 cancel, so we forget about that. And there's no way I can make a 1-mer if my minimal mass is 1, then I can't make 1 from anything, so there's no gain term. So the loss term is minus C1, and then I have the sum 2. So I guess I should put here a minus 2 C1 sum Ck. And I'll define this thing to be minus 2 C1n. So n is the density of clusters of any size. C2 dot is equal to, so we put a 2 and 1/2 that cancels, I have C1 squared minus 2 C2n. C3 dot is equal to, so again this cancels and I have a term which is 1, 2 and 2, 1, so there's 2 such terms, so I'll have the 2 C1 C2 minus 2 C3n. Maybe I'll write one more equation, C4 dot is equal to, so there'll be a 2 C1 C3 plus C2 squared, note the different factor in front of it, minus 2 C4n, dot, 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 dot. So if this is a course in differential equations, I could give this as an assignment and say, okay, solve these differential equations. And in fact, we're going to see how you can solve them. But one thing that one often does to try and get some partial information to get a feeling for what's going on is instead of looking at the full equations themselves, let's look at the equations for the moments of the distribution. So let me define the nth moment of the mass distribution is equal to the summation k to the power n ck, summed over all k. So the first moment you might think is like the average mass. In fact, that's wrong, but we'll see why in a moment. But these moments are sometimes easier to deal with than the full master equations themselves. So let's look at the equations for the moments. So let's write the equation for m0 dot. So what I'm supposed to do then is I take ck dot, multiply by k to the 0, which is 1, and just sum it up. So I go back to my original rate equation here, and I'm going to multiply by k to the 0, which is 1, and then sum over all k. And let's see what happens. So for m0, the 2 and the 1/2 cancel, so I have sum ci cj with the restriction I plus j equals k. But when I sum over all k, that removes this restriction, and so I get the unrestricted sum here. Summation sum ci, summation cj. The two sums have been unrestricted. And then on the right-hand side, I have minus, so k is 2, and then I have sum ck, and then I have also sum ci. So we have here sum ci, sum ck, which is n squared, minus 2n squared. So this is minus m0 squared. So immediately we get m0 is equal to 1 over 1 plus t. And in writing this last equation here, I'm making the assumption of starting with a monomer-only initial condition. So it's a very natural starting point for aggregation. I start with a gas of monomers, or a collection of monomers, and see how they evolve with time. So the total number of clusters, I've used the term, I should say I've made a little bit of a faux pas perhaps, that the density of clusters is the same as 0 at the moment. So I'm using them interchangeably. Let's look at m1 dot. So if I look at the first moment, So I have to multiply now by k to the power 1. So I'm going to write here, I go over to this equation. Kij is 2, so the 2's going to have cancel. And I'm going to have I plus j, that's what k is, times ci, cj. And this is sum over I and j, unrestricted. And then I have minus summation kck summation ci. And over here, ICI is the first moment, sum Cj is the 0th moment, so I have M1, M0. I have two of these guys, so I have twice M0, M1, 2 M0, M1, minus, and here is, I forgot my 2 here. Here I have M1, M0, so minus 2 M0, M1 equals 0. So we learned something very obvious in hindsight, which is that the first moment is conserved. And so I can define it to be equal to 1, for example, because it's time independent. So the average cluster size is actually just a constant here because it's just counting the total amount of mass in the system. But look at M2 dot. So let's do that now. So I'm going to take k squared, sum ck, but k squared I'll write as I plus j, and so what I'm going to have when I do the summation is ij, unrestricted. I have I plus j squared ci cj minus 2, and then here, when I take the second moment, I'm going to have k squared ck sum ci. So when I expand this product, there's there's several sets of terms. There's an I squared ci cj, a j squared ci cj, which is nothing more than m0 m2 with a factor 2, which cancels the 2 m2 m0 here. And all that's left is the cross term, which is 2 ij ci cj, which is 2 m1 quantity squared. So I get 2 m1 squared, which is equal to 2. So therefore, I find that m2 is equal to 1 plus 2t. So I just integrate this equation. And at t equals 0, I should get the total mass is 1. If I'm choosing a monomer-only initial condition, then the total mass of the system is 1. So what we learned from this thing is, in fact, that the second moment is a natural scale for the size of the clusters in the system that grows linearly with time. And in fact, you can now play this game as many moments as you want, and what you'll see, in fact, is that, in general, m to the n is scaling like t to the power n minus 1. Yeah, Ben.
The initial condition for M2, where did that come from?
The initial condition came because my ck at t equals 0 is just equal to delta k1. Just a delta function. And so therefore, all the moments are 1 and t equals 0. Okay. So, anyways, this is sort of beating around the bush because we haven't solved anything yet. We haven't solved the problem. So what I want to now introduce to you is a very powerful and very beautiful technique known as the generating function. And this turns out to be the incisive way to attack problems of this type. And in fact, in hindsight, again, a lot of these things, when you develop the right apparatus, are really quite straightforward. The point here is that when you write down this original master equation, the fact that the two indices here sum to k, this mass conservation, this is called a convolution. Presumably most of you know this terminology, convolution. And because it's a convolution, it should cry out to you, and those who've been in my class at BU are probably sick of hearing this message, this should cry out to you that you should do some kind of a transform technique. In the case of, say, something which is defined in a continuous space over plus and minus infinity, you would do Fourier transform, and you would change a convolution to a product. If it was defined over a half space, you would do a Laplace transform, and you change the convolution into a product. So the generating function is nothing more than the discrete analog of the Laplace transform. And so if you've not seen the generating function before and it seems intimidating, just think Laplace transform, because it's really nothing more than a Laplace transform. So I'm going to find a function called c of z is equal to summation ck of t, c to the power k equals 1 to infinity. And for those of you who have not, how many people have seen the generating function before? Most people. Okay, very good. If you haven't seen it before, a very nice exercise to do is to work out the nth term in the Fibonacci sequence using the generating function technique. And you can solve the recursion formula in a very nice way with this. So anyways, I'm now going to use the generating function and apply it to the master equations. So when we take our master equations here, so let me just write them out explicitly for constant kernels. So we have ck dot is equal to summation ci cj, I plus j equals k, minus 2 ck sum ci. Now what I'm going to do to these equations then is multiply them by z to the power k, sum from k equals 1 to infinity. And so on the left-hand side, we're going to get c of z dot. And on the right-hand side, the first term here, we have I and j, but they add up to k. So I can break up this k is equal to I plus j. And so I have ci zi, cj zj, which is nothing more than the generating function squared. So I get c of z squared. And here I have 2 ck zk, so that's minus 2 c of z. But then I have some ci without any z, and that's nothing more than the generating function at z equals 1. So this is c of 1. So it looks a lot simpler. We've taken an infinite set of master equations and reduced it to a single differential equation. And this is really quite a striking feature that comes because we've converted a convolution into a simple product. Unfortunately, the equation isn't quite closed because we started with c of z and we end up with c of 1. But the thing is that what you can then do is just substitute c of 1 here, and you get c of 1 squared minus 2 c of 1 squared. And so this is equal to minus c of 1 squared. So if you take these two equations and just subtract them, so let me put that over here. Let me define the difference between c of z minus c of 1. Let me just call that c minus, as in my notes. So c minus dot. And then you see I have c squared minus 2c of 1 plus c of 1 squared, which is nothing more than c minus squared. So, a lot of these nonlinear problems, like the trick is if you find the right transform technique, you take something which looks fairly formidable, and with just a little bit of the right transform technology, one can transform it into a very simple equation. Just this. And the solution to this equation is c minus is equal to c minus at t equals 0, 1 minus c minus at t equals 0, t. That's all there is to it. And so all we have to do then is substitute in what is c minus at t equals 0. And so we just plug in when t equals 0, we have the delta function here. So c at t equals 0 is just z. C minus is z minus 1. You plug it into here, so you're going to get z minus 1, 1 minus z minus 1, t. Yeah.
Can you repeat what this c minus object is? How did you
I just took the difference between c of z minus c of 1. That's what c minus is. Yeah, so c minus here is equal to c of z minus c of 1. That's all. Anyways, and so now what you do, because what we want is ck of t. So what we need to do is expand this in a power series in z. And I'm not going to do that because it's all straightforward. And at the end of the day, when you expand this thing in a power series in z, here's the final answer. Ck of t is equal to, what is it? It's t, it's t to, I'll get it right, t to the k minus 1, 1 plus t to the power k plus 1. So that is the answer for the cluster size distribution. Yes?
Where did you get c minus at t equals 0?
Well, so c at t equals 0, I use the fact that the initial condition was a delta function. So I'll put a delta function here, so c at t equals 0 is just z. And c minus, I have to subtract at z with z equals 1, so I get z minus 1. Okay, so the thing is that it's a nice exact solution, but let's get some physics out of this, because oftentimes with these exact solutions, in this particular case, it's sufficiently simple that you can intuit everything. But I want to show you how to recast it as a scaling form because it's so useful. So we have the ck of t. Let me write it in the following way. 1 over 1 plus t squared, t divided by 1 plus t, all squared. And so in the limit, as t goes to infinity, all right, this is 1 over t squared. But now what is t over 1 plus t? I can write this as, so divide through by t, I'll get 1 plus 1 over t downstairs, which you can write as 1 minus 1 over t upstairs. K. K minus 1. K minus 1. Thank you. And then this I write as 1 over t squared e to the minus k over t, which I can write in the following way, 1 over t squared e to the minus k over k star. So k star is a characteristic cluster size that comes from this distribution, and you see that k star is proportional to t. So that kind of fits with this picture here that the second moment of the distribution is the natural measure of the average cluster size. Now, one more thing before I leave the constant kernel problem is let's just sketch this to get a feeling for what's going on. So let me now plot here ck as a function of t, and let me also plot ck as a function of k for different values of the time. So first of all, I look at ck as a function of t. So if I start with a monomer-only initial condition, so the monomers start at 1, and so according to this exact formula, monomers, this goes away, I just get 1 over 1 plus t squared. So they're going to fall off something like this. So this is C1. Dimers, so k equals 2, this is linear for small t, but then eventually this factor goes to 1, and it eventually goes to 1 over 1 plus t squared. So dimers come up linearly and eventually follow the common curve. So here's what C2 is doing. C3, again, k minus 2 here means that for small time this goes quadratically with time, and so it's doing something like this. So here's C3, etc., etc. And now if I ask, well, what is the distribution at some fixed time? So at an early time, I just look at my distribution. I just go down a vertical path, and I have lots of monomers and almost nothing else. So at early time, the distribution maybe looks something like this. So this is for T1, a short time. At some intermediate time, say over here, then I have monomers, dimers, trimers, 4, 5, 6. They're all very close to each other. But then eventually I get to a point where, say, C20 hasn't yet appeared because it's the 20th, 19th order curve, and I'll get a cutoff something like this. So this is at a value T2 greater than T1. And at later times still, one gets maybe something like this, T3 greater than T2. And so the distribution just broadens and broadens and gets, the amplitude decays away. And the point here is that if you just look sort of at a dimensional analysis perspective here, the area under the curve is the total number of clusters. And we can figure that out because this here is roughly 1 over t squared. That's the common value at which these cluster concentrations approach. So the height of this curve is 1 over t squared. The characteristic size is of the order of t. That's where the cutoff occurs. And so the area under this curve is proportional to 1 over t. And that was what we had over here, that the 0th moment, the total number of clusters decayed like 1 over t. So everything hangs together in a very satisfying way for this constant kernel case. So, any questions on this story before I continue on? All right, I want to now turn to the much more spectacular example of the product kernel. And here we're going to learn that the product kernel, even though it looks very innocuous at first sight, is just mind-bogglingly more interesting. And the solution methods are also similarly quite interesting itself. So let's now talk about the product kernel. So I'm going to assume now Kij is equal to Ij. It turns out that in this whole field of aggregation kinetics, there's just a very few set of kernels that are exactly soluble, and the product kernel happens to be one of them. And the motivation for the product kernel comes from the phenomenon of gelation. If you imagine when you make Jell-O, you put powder into the water, you put it in the bowl, and so you start with a liquid, and then the next morning out comes something which is sort of solid, at least it doesn't pour. And what's happened is that the elemental units in the Jell-O molecules are multifunctional arms that have lots of grabby end groups. And when the grabby end groups grab their friends, then there's more grabby end groups, and they get more and more grabby as time goes on. And if you think just of a simple physical picture for what the molecules look like, it's easy to motivate a reaction kernel which goes like IJ. So I want to now study the master equations for this process. So let's look at CK dot. So again, it's going to be equal to 1/2 summation. And now because there's the reaction, the kernel IJ, there's going to be an ICI, JCJ in the gain term, and then there's going to be a minus summation over all k. So this was I plus j equals k. This is a sum over I. And then I'm going to have a KCK ICI. Now, one important thing that simplifies this equation a little bit is that the summation ICI, that's just the total mass in the system. And in fact, for those of you who are experts in this field, you'll notice there's actually a little sleight of hand here. But let's assume that we don't have any experts in the audience. So the sum ICI, well, that seems like it's a total mass, which I can set equal to 1. So let's forget about it. And so I can write this as equal to 1/2 summation ICI JCJ minus summation KCK. So this is CK dot. So let's now try and solve this by the same generating function technique. And in fact, this generating function technique is the right way to deal with this equation. So I'm going to take this equation, multiply everything by some factor, and then sum up, and yes?
In the first equation, the sum is just over I, right? So in the second term, in the second line, there's no sum line.
Thank you.
And there is no K there. There's no K.
Did it?
There's no K there.
ICI,
JCJ. Yeah, that's another problem of mine, is that I'll say J and write K, so keep me honest. Okay, anyway, so that's my equation. I want to apply the generating function. Now, the thing is that because of these factors I sitting out in front, if you look at the generating function, if I put like a K in front of here, you can do some rigmarole with differentiation to bring down a factor K, but then there's a factor K minus 1 sitting here. And so with malice aforethought, like after you've done this a few times and you realize it's the wrong generating function to use, what I'm going to do here is the so-called exponential generating function, which is nothing more than just the generating function itself, but in a slightly different variable. I'm going to multiply by e to the y k and sum from k equals 1 to infinity. Why I use e to the y is because then you're going to see very quickly that I generate derivatives in a very natural way. So on the left-hand side of the equation, let me call e of y, the exponential generating function, summation ck e to the yk. So e for exponential. So what I have on the left-hand side is ey dot. And in fact, now I have to be a little bit careful because there's several variables in the problem. There's k and y. And so what I really mean here is dEy by dt. It's a partial derivative with respect to time. And so this ey actually has time dependence in it, because there is a time dependence in ck. So let me now be just a smidgen careful here. On the right-hand side, because k is I plus j, I'm going to have e to the yi, e to the yj. But then what is ICI, let me do a little worksheet here. ICI e to the yi, summation over all I. Well, that's nothing more than the generating function, but differentiated with respect to y. So, so now it looks like, well, something a little unhappy is happening here because I have the derivative with respect to y. And so the thing is that now that you see that I deliberately, you might think that I was faking it, but I stumbled into something here. And what I'm going to do is, you see that this choice of the generating function, we have the generating function this side, then we have a product of partial derivatives, and it just turns out to be horribly messy. And so, in fact, I'm not going to use this generating function. But again, it's one of those things that after the fact you learn better. Now let me define it kck e to the yk. Let me try that. So I'm going to take this equation, multiply also by a factor of k. And let's see what happens now. So on the left-hand side we have this. On the right-hand side, so let me now do a little worksheet for, say, this first term. So we're going to have 1/2 summation I plus j, I, ci, j, cj, e to the yi, e to the yj. So there's two terms which are essentially identical because there's an I squared ci, jcj, and there's a term j squared cj, ici. They're the same thing. So we can forget about the 1/2, and I can write this just as summation, for example, I squared ci, jcj, e to the yi, e to the yj. Cj, thank you. The second term is just the generating function. The first term is just a generating function with an extra factor of y, which is just a derivative with respect to y. So what I have here then is e of y dey by dy. And the 1/2 has been cancelled out. And then what is the last term? kck e to the yk. Yeah, so this is nothing more than dey by dy. So that's the equation I have to solve. So let's just look at this equation by itself. So what we're going to have then is dE by dt, I'm going to stop writing the arguments, is equal to e minus 1 dE by dy. This is the Berger's equation in disguise. Some of you may recognize this from nonlinear wave propagation phenomena. This is nothing more than the good old Berger's equation of nonlinear wave propagation phenomena. And the thing about this equation is that it's a first-order nonlinear partial differential equation. And so usually we learn how to solve linear partial differential equations. And so this looks a smidgen intimidating. But it turns out that it's actually not so intimidating. The easiest way to solve this equation is by a method called the method of characteristics. And the method of characteristics is nothing more than essentially the integrating factor from freshman differential equations, but for multivariate situations. So the idea here is, let me write this, is dE by dt minus, let me write it as plus, 1 minus e dE by dy is equal to 0. And on this side, I'll write this as nothing more than the total time derivative with respect to time. So I have, and so what is the total time derivative with respect to time? This is nothing more than dE by dt plus dE by d plus dE by dy, dy by dt.
So maybe, is there any reason you can't just change e minus 1, call it a new variable, to count that by 1?
You could do that, but I mean, I think this will work just as well. But the point here is that notice that by writing it in this form, and when I write it as a total time derivative, there's the partial derivative with respect to time, and then there's a second thing. And so if I choose, if I go along a trajectory in the yt space defined by this, then this thing is a total time derivative which equals 0. And so on these curves called the characteristic curves, the function doesn't change. So we have, when dy by dt is equal to 1 minus e, then e is constant. And so that says that along this curve, e is constant. So now we can integrate this equation. We get y is equal to 1 minus e t plus some function of e, which is the initial condition. And the initial condition, again, if I start with a monomer-only initial condition, then at t equals 0, I only have 1 c1 e to the y 1. So e to the y is my initial condition. So at t equals 0, I have that e is equal to e to the y. So at t equals 0, y is this constant f of e, and I have to write it in terms of e, and so that says that y is equal to log e. So at the end of the day, my solution is y is equal to 1 minus e t plus log e. That's the solution to the problem. I mean, it maybe seems a little bit like black magic, but that's it. So if I exponentiate this, I'll get e to the y is equal to e to the 1 minus e t e. And so let me write this as e to the minus et is equal to e to the y minus t. That is the solution for the generating function itself. The only bad thing about this is that it's a implicit relation because I don't have e explicitly. I have e times e to the et is something. And what we want to do is find the generating function and then write it as a power series representation. And so that looks also impossible, but it turns out that we can stand on the shoulders of Lagrange, who told us how to do these sorts of things. And so there's this piece of black magic called the Lagrange inversion formula, which I'm not going to repeat here because it's in my notes. But the point is that there exists a way of going from f of e is equal to some variable and turning it backwards and making e as a function of that variable. And so, if you want to see me do it like offline, I'm happy to do it, but it's spelled out of the notes, and it's just one of those things. The first time I learned it, I was just stunned at how beautiful this was. And so sometimes things from complex analysis can be very valuable. So anyways, the point of all this is that it is possible to write e as a power series in this basic variable, an expanded power series, and at the end of the day, one ends up with a very remarkably simple formula for the cluster mass distribution. And so it is the following thing. It's k to the power of k minus 2 over k factorial, t to the power of k minus 1 e to the minus kt. So it doesn't look much more intimidating than that of the constant kernel. But the thing is that hidden inside of this formula are some wondrous properties, and the gelation phenomenon is contained inside of this simple formula. So let's look at this in a little bit more detail. Let's look at asymptotic behaviors. And the way that one would do it again is let's apply Stirling's approximation. And so I'll write this as k to the k minus 2. So Stirling's approximation says here is k to the power k, e to the power k, and then there's going to be a square root of 2 pi k. So that's the leading behavior in Stirling's approximation. T to the power k minus 1, e to the minus kt. And so just one more line here. So we factor, this cancels, and we're going to get 1 over square root of 2 pi, 1 over k to the power of 5 halves, and then I have e to the minus. And so let's write here k. So there's a power t. There's minus, well, let's put the 1 later. Then I have t to the power k minus 1. And so for large k, since that's what we're interested in, let's forget about the k minus 1 here. And so I'm going to get here log t minus 1. So that's the answer. So this is, again, approximately equal to. And so there's several things about this that are really quite remarkable. So first of all, so for t less than 1, the coefficient sitting up in here is a positive number. And so we have an exponential decay of the cluster mass distribution. And in fact, if we expand, so let's write t is equal to 1 minus epsilon. So you plug t is equal to 1 minus epsilon here. The 1's cancel. We have an epsilon here. We expand log t. We're going to get epsilon, which cancels that guy, and then an epsilon squared over 2. And what we're going to get then is 1 over the square root of 2 pi, k to the power of 5 halves, e to the minus k, 1 minus epsilon squared. I'm sorry, 1 minus t squared. So this is a scaling form for the cluster mass distribution, and you see that it decays exponentially with mass for large mass. At t equals 1, all this goes away, and you just get 1 over square root of 2 pi, 1 over k to the power of 5 halves. So one gets a power law distribution of cluster masses. So it's quite impressive that as you change from t equals less than 1 to 1, the distribution goes from exponential to power law. And the fact that the power law exists is a signal that something weird is going on. In fact, it's a phase transition to gelation. And then for t greater than 1, the exponential then magically again becomes positive here, and one gets, again, 1 over the square root of 2 pi, 1 over k to the power of 5 halves, e to the minus k over k star. So that is a solution for the product kernel. Yes, question?
You said this captures the transition, but so you have a power law for only at t equal to 1. So that's telling you that something is critical happening.
Right, and I'm going to tell you what's happening right now. Okay, so the fact that something weird is happening at 1, let's try and analyze that in a little bit more detail. And so there's a very simple equation that describes the gelation phenomenon itself. So let's look at gelation. So we thought, or I kept always saying, well, KCK is equal to 1, which is essentially summing up the mass of each cluster times the concentration of each cluster, which is just the total mass of the system. So if I sum it up, I ought to get 1. However, this sum, when I do like sort of, I don't know what you call it, Riemannian summation, it doesn't include the term at infinity. If there was a term at infinity, that's not included in this sum. So this sum is typically 1, but sometimes it's not 1. And it's not 1 when a gelation occurs and there's an infinite cluster. And so, in fact, this is a crucial sort of equation. You have to sort of stare at it for a second to believe it's true, that when gelation occurs, this is summing the mass of all finite clusters up to arbitrarily large size, but it misses the infinite cluster. So the sum of the infinite cluster and the mass of the infinite cluster plus that of the finite cluster is equal to the total mass of the system, which is 1. So that is, but now let's figure out, what is this G? I just sort of postulated it. And the way that we figure out what G is let's go back to this equation over here, and let's evaluate it. So let's call this equation 1. So we've only had one equation so far in this talk. Let's evaluate 1 at y equals 0. So unfortunately, I just erased my generating function. Let me put it back again. E of y is equal to summation k ck e to the yk. So at y equals 0, it's just k ck, which is just 1 minus g. So what we're going to have then at y equals 0, we're going to have 1 minus g, and then I have e to the minus 1 minus g t, and that's equal to e to the minus t. So this cancels that, and then I have 1 minus g is equal to e to the gt is equal to 1. Or I can write this as g is equal to 1 minus e to the minus gt. This is a remarkably powerful equation. It looks so trivial, but it has a lot of meat to it. And it essentially tells you what's going on with the gelation phenomenon. So how do we solve an equation like this? We don't solve it because it's a transcendental equation, but we solve it just by graphical analysis. And so if I plot as a function of g, the left and right-hand side of this equation, so the left-hand side is just g, so it's a straight line of slope 1. The right-hand side, well, at g equals 0, this is 1. 1 minus 1 is 0. It starts at 0. The initial slope of this function is exactly t. And so at t less than 1, it starts off with a slope less than 1. And so there's only a single solution, g is equal to 0. There's no gelation. But when t is larger than 1, it starts off with a slope bigger than 1. And so there are two solutions. One where there's a non-zero gel phase and one where there's no gel. And this is very much like the same solution that one gets in like the Curie-Weiss effective field theory, when one plots a hyperbolic tangent m versus n, and you solve it graphically, and there are two solutions, and this is the interesting solution. And the thing is, you can't solve it explicitly, but if you just perturbatively look at this, the result of this graphical analysis is that g has the following behaviors as a function of time. It's equal to 0 for t less than 1. It's equal to something like 2, 1 minus t, for t approaching 1 from above. And it's something like 1 minus e to the minus, well, I guess I should look at my notes. e to the minus t as t goes off to infinity. So at infinite time, everything is swallowed up in the gel phase, and right at the gelation point, one has this tiny little gel fraction, which, sorry, backwards here, 2t minus t minus.
Question.
Fire away.
I'm really confused. So normally in gelation you tweak the number of bonds you're making, which would be your K, your big Kij. What is the rate of aggregate? What is the rate? I mean, there's Ij, right? Kij is equal to Ij, but there's some constant before that.
That's right.
So normally you would tweak that.
No, you don't tweak that. That's an irrelevancy in the model. The crucial. So if your question was Kij, you'd like to write this as constant times I times j. What is this constant?
Well, normally in gelation you would precisely say that you're increasing the number of bonds that's possible between.
Right.
It's not a time-dependent phenomenon usually, right? You're talking about equilibrium gelation, say.
Well, no, but I'm not talking about equilibrium gelation. I'm talking about specifically a non-equilibrium process of irreversible aggregation and an infinite cluster appearing in a finite time.
Maybe like you're in a state where you would, in equilibrium, you'd have a gel state. You have a gel.
No, but that's the confusing part. You always going to have a gel phase here at infinite time. It's not a transition. You're always going to have.
So he's asking if maybe is there a parameter in the model, maybe not in this model, where you can avoid gel state at any time?
Well, so if the next part of my talk, you're going to specifically come to that question. What is the conditions on the reaction kernel such a gelation occurs? I will explicitly answer that. So there's three questions. You first, I guess. No. One further back.
I'm wondering about the fact that we solved the non-mass surface, right? Because we assumed that the sum on KCK was 1
Right.
to derive the generating function of everything.
No, actually, all of this stuff, everything up to right here was for t less than or equal to 1. So everything is kosher. This was a little bit unkosher because I assume t is larger than 1. But in fact, because there's only like one gel cluster, the concentration clusters is sort of depleted by 1 for that one infinite cluster. So everything is actually okay for that.
But
This
we're
part,
looking at G.
right?
Yeah. You're looking at what happens with T greater than 1.
That's right.
T greater than 1.
That's right. Yeah. So, but the thing is that if I wanted to start with the original mass equations, that sum that I said was 1, I should replace by 1 minus g, and you can do that and work out all the details, and it's done in my notes. So there was a bunch of other questions. Just shout out.
What's the physical meaning of G growing? I understand non-zero G means infinite cluster, but what does it mean for G to grow?
Well, so what you should think of here is that as a function of time, the gel fraction, so it's 0, 0, 0 until you get to 1, and then the gel fraction grows. It grows linearly in this mean field theory, and then eventually it covers everything, all the mass. So this is kind of like a percolation transition. You start off with small clusters, they don't span the system, then there's a spanning cluster that encompasses zero mass at the transition itself, but then eventually encompasses everything.
So G is just gel fraction.
Exactly, the gel fraction. Yes?
How is your original equation to work with non-zero G? Because we have this reaction with increased cluster, which wasn't in the
Yeah, so, okay, let me write it out. So it's really, so all I have here, so I had some ck dot, so it's equal to summation 1/2 I ci j cj, and then I have minus ck, and then what I had here was some ici. That's what I had originally, ici. And so all I'm doing here, what I should put here, is I should put 1 minus g.
What about the first term? There is somewhere C infinity, which is
No.
finite.
No.
Right?
No.
But it's there, right?
No, but the thing is that here, when I did this, I made the assumption some ICI equals 1. But now I don't make that assumption. I just say this is 1 minus g. But I'm not summing, this is a constrained sum here. I'm not summing freely to infinity. So there's no funny business with this term. Trust me, it's true. Yes, Kim.
So you actually don't want the 1 minus g there, right? Because you can have a loss to the gel.
You can't have a loss to the gel. So for t greater than 1, this term is here, and then you have to worry about loss to the gel. So, but it's not a big deal because it doesn't affect the number of clusters very strongly because there's only one cluster. I'll have more to say about it in just a minute. So questions in the back?
Yeah, so T equal 1 is where everything happens. So.
Right.
So can you relate T, like the time to the Kij? I mean, like, what is T in units of?
Yeah, well, so that's true. I mean, everything has been engineered because the constant in front here was equal to 1. So I made the time equal to 1. So, I mean, if I really want to be kosher about it, I should go back and put in the dimensional units. But everything's been non-dimensionalized.
So it's in terms of that constant.
That's correct.
Okay.
That's right. Yes.
Just trying to understand the physics of this. Why do you call this gelation? I mean, why is this? What's the physics? Yeah, basically, I just don't know why it's called gelation.
Well, because the point is that there's a finite fraction of the, I have an infinite system. I have like the entire universe is filled with an infinite number of clusters, and there is one cluster that contains a finite fraction of all the mass. That's why it's called gelation.
So it's going to be called percolation.
Yes, you can think of it as percolation. Yeah, question.
Yeah, just going back to the basic phenomena of gelation. I mean, are you assuming it's like a two-dimensional?
I'm not assuming a two-dimensional system. I'm assuming here a mean field. So there's just a gas of clusters, and any cluster can react with any other cluster with equal facility. So you should think of it as a zero-dimensional system because there's no space here. You have just a collection of clusters. You pick two clusters at random and join them together and do this process over and over again.
So it doesn't depend on the surface of the gel.
Well, once I fix a reaction kernel, then the geometry is all sort of subsumed into the reaction kernel itself. So I'm having I'm basically talking about a non-geometric process. I'm just picking I have these gas of clusters and just interacting them bimolecularly. Maybe I should go on. I mean, what should I do with finishing up? Because I have. Well, I would say that I could finish my last topic with scaling in 5 or 10 minutes, and maybe that would be a natural stopping point, and then maybe. Yeah, I mean, unless someone has a really burning question, let me.
Can you just quick question? I mean, can you still solve that equation even though G is function of time, unknown function of time?
Yes, you can do it approximately. I mean, this is actually sort of not fun because this is ugly, but yes, you can do it. I mean, and it's something that I'm not prepared to do right now, but
no,
it can be
question
done.
whether you can.
Yes, it is doable. Okay, so there was a very good question about why about gelation, why did it appear for this kernel? And so I want to spend the last 5 or 10 minutes very briefly talking about a scaling approach because there's this cynical thing like those who can do research, and those who can't become administrators. So it's the same kind of thing here. When you can solve the problem, you solve it. When you can't solve it, you do scaling theory. So scaling theory is like the administration of solving an equation. So let's do scaling. So the point is that it turns out that for aggregation kinetics, there's only a very few set of reaction kernels that can be solved exactly. If you can't solve it exactly, what do? And so the idea is you try scaling. So let's write the scaling ansatz, which probably some of you have seen before, which is that, let me write CXT. Well, the thing is that if I wait for later time, it's clear the clusters are getting bigger, and so I wait longer, the clusters are getting bigger still. And so it seems natural that if I rescale the cluster size by an appropriate power of time, that I could get a distribution which will be time invariant. And so the idea here is that one writes this as some function of x divided by a characteristic cluster size s. So s is a characteristic cluster size. One makes this ansatz that the two-variable cluster size distribution is a function only of a scale variable. This statement, though, is incomplete because it misses one important feature that you want to have that the total mass of the system is conserved. So if you want to enforce mass conservation, x c x t dx is equal to 1, for example. The only way that can happen is you put a factor 1 over s squared here. And then you can immediately verify that if you integrate this thing dx, here I have x, fx over s dx. There's 2 powers of x here, which get canceled with the 2 powers of s downstairs, and so this thing is order 1. So,
S is a function of time.
Pardon me?
S is a function of time.
S is a function of time, that's right. So S is equal to S of time is a characteristic cluster size. And so what I want to do now is to write down what is the consequence of the scaling ansatz for a general cluster aggregation process? So in order to do this, I need to go from a discrete formulation to a continuous formulation. So let me write CXT dot. So now I'm talking about clusters of mass x, which are continuous at time t. And so they'll do something like this: 1/2 integral from 0 to x, k, y, x minus y, cyt, cx minus y, t, dy. So this is the gain term, that a cluster of mass y comes to a cluster of mass x minus y and make a cluster of mass x with this rate. And then there's a corresponding loss term, minus 1 over from 0 to infinity, k x y cx cy. So as it stands here, this is a nonlinear integral equation in two variables. It doesn't look very pleasant to solve. And the point of scaling theory is that it allows you to do variable separation, so you can separate out the dependence on the scaled variable and the dependence on time, and then you have two separate equations. One equation turns out to be trivial, and you can easily understand what is the criteria for gelation. The other equation is still difficult, but at least you solved half of the problem. So that's sort of like scaling theory is a little bit of a cop-out here, because you solved only half of the problem. Anyways, the point here is that in order to make any progress here, we have to focus attention a little bit on what is the functional form of kxy. You can think of kxy schematically as like an infinite dimensional matrix. Here's k11, k22, k23 all along the diagonal, k11, k12, k13, dot, 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 dot. And the way that I want to think about it schematically is that out here you have interactions of large clusters with other large clusters. Here you have small, small interactions. Here you have small, large interactions, large, small interactions. And it turns out that there is only two features. This is now on the basis of like 30 years of people doing research in the subject. There's only two basic features of this infinite matrix that affects the asymptotic properties. There's a so-called homogeneity index and another index that I'm going to define momentarily. But the point here is that there's two characteristics. There's the homogeneity index lambda, and this is defined by k ax ay is equal to a to the power lambda kxy. Let me just worry about this one since I'm running out of time, and let's just investigate what is the role of the homogeneity index on all of this. So what I want to do now is let's take the scaling ansatz and apply it into this equation. Let's also use this homogeneity index and see what comes out. Let me just point out that for the constant kernel case, lambda is equal to 0. For the product kernel, k, if it's ij, then this is lambda is equal to 2. So those are the two cases we've discussed so far. And what we're going to see now is what happens as a function of general lambda. So the idea here is that we want to take the scaling ansatz, shove it into this equation, and try and separate out variables. And so let's do each of those pieces in turn. And I promise to do this in 5 minutes. So C dot. So according to the scaling ansatz, I differentiate 1 over time, so I'm going to get minus 2 over s cubed, s dot, f of x over s. But then I have to differentiate inside of the integral, so I get minus 1 over s squared, or plus. Then I have f prime of its variable, x over s. Differentiate inside the variable, so you get minus x over s squared, s dot. So if I gather everything up, I'm going to get s dot over s cubed with a minus sign, 2f plus u f prime of u. So I'm now calling the scaling variable just u. So that's the left-hand side. On the right-hand side, there are two similar terms. Let's just focus on this one. By the way, there's here an integral is dy. Let's just focus on the second one. So we're going to have integral from 0 to infinity, okay, xy. So cx, so it's 1 over s squared, f of x over s, 1 over s squared, f of y over s, dy. So it's clear why I want to rewrite this in terms of scaled variables. So to do that, let me put here x over s, y over s. And according to this homogeneity assumption here, that's the same as putting here s to the power of lambda. And so here I'll take one of the powers of s and stick it over here. And so what I'm left with at the end of the day is s to the lambda minus 3, integral from 0 to infinity, k of x over s, which is u. Let me call y over s v, and then I have f of u, f of v, dv. So if I come back over here now, let's forget about this for a moment. So here what we have is minus s dot over s cubed, f, we have 2f plus uf prime. And on the right-hand side, I'm going to have 1/2. And first of all, notice there's this s to the lambda minus 3 that I have in coming out of the scaling of this term. By dimensional analysis, and also I'll leave this as an exercise for you, there's the same factor s to the lambda minus 3. So let me write here s to the lambda minus 3. And then I have some horrible integral operator, which is the sort of the scaled form of everything you see here. But the crucial point, and here is the punchline, is that I can now separate out variables. I have s dot over s to the power of lambda. I'll bring that s over here, is equal to, put the minus sign over here, this horrible integral operator, k of u, divided by 2f plus uf prime. This is a function of time only. This is a function of u only. So just good old separation of variables. These are separately equal to a constant. Let me define that constant. Put the minus sign over here already. Let me define this constant equal to lambda, the separation constant. And so the point of the scaling ansatz is I took a two-variable integral equation and separated out into something which depends on time only and space only. And since I promised to be done in now 2 minutes, I'm only going to worry about the time dependence and punt on the space dependence. But what we find from this, if I just solve s dot is equal to lambda s to the power capital Lambda s to the little lambda. This has 3 solutions. If lambda is less than 1, one gets s of t, scales as t to the power 1 divided by 1 minus lambda for lambda less than 1. It goes like e to the capital lambda t for little lambda equal to 1. And it goes like 1 over t gel minus t for lambda bigger than 1. So this is the important result of this whole story here, that one sees that this homogeneity index plays a crucial role in deciding what is the asymptotic behavior of an aggregating system. If the homogeneity index is larger than 1, one gets dilation in a finite time. If the homogeneity index is less than 1, one gets power law or scaling behavior, and only at lambda equals 1, one gets this weird exponential scaling. So the reason I punt on the second part of this is that this is still a differential integral equation, but in one variable. And for simple enough problems, you can actually solve this equation explicitly. In the case of aggregation kinetics, this equation has not been solved explicitly, but what one can do is solve it asymptotically in the large U limit, the small U limit, and there's various other principles people have been able to try and apply to get some partial information. But nevertheless, this part of the problem still remains rather, I'd say, unsolved. So I think I've run over a few minutes, but I think I'm done for now.
Okay, thanks. Well, you can take your revenge on Sid and sit at his table and make sure he doesn't get to eat. So we'll take a couple of questions and then we'll break for lunch.
So your homogeneity index is kind of scaling your stickiness. I mean, your basic problem had some stickiness coefficient, right?
The crucial thing about this homogeneity index is telling us how the stickiness depends on the mass, not an intrinsic stickiness, but just how it depends on the number of constituents in the cluster.
So really, there are 2 kinds of transitions you're talking in one go. I mean, one you have if you scale your stickiness up, for any time you're going to see either infinite cluster, infinite time you're going to see either infinite cluster or you're going to not see one.
I mean, I don't know what you mean by scale the stickiness up.
I mean, your lambda, for example, is really telling you how reactive your colloids or whatever particles are. And beyond a certain lambda, for any time, for infinite time, you're always going to see infinite cluster.
Correct. And so the thing is that this thing says that when T is mathematically infinity, then I'll have an infinite cluster. But the interesting thing is whether you get an infinite cluster at a finite time. That's the crucial difference between the gelling kernels and non-gelling kernels.
But you also have the case when your lambda is small enough, you would never get infinite cluster, right?
Correct.
So, okay, I'm happier with that gelation.
Okay.
And it's 2, just lambda is 2 is the case you consider.
That's right. And so it's really in the gelling regime.
And is that asymptotic as a small t, t minus tg, right?
Did I get it backwards? This is right. This is forwards. This is for t equals 0. The size starts on something and then it blows up.
Oh, absolutely.
Yeah.
I'm confused about what the correct master equation should be beyond the gelation transition, and this was already brought up.
Right.
And you wrote down 1 minus g, but I don't see why that would be the correct thing to do.
Because the thing is that there's only one place in the equation where I had an unrestricted sum ICI. So by construction, that sum is equal to 1 minus g. But everywhere else in the equation, I did not have an unrestricted sum ICI.
But then you're not accounting for the loss to aggregate onto the super percolation cluster.
No, but the thing is that there's the gain term, and by construction, if I'm looking at the gain of any finite-sized cluster, then it doesn't have anything to do with the infinite cluster. It's only the loss term where it can interact with the infinite cluster. So it's been properly accounted for. You don't believe me? You'll sit at my table.
Yes. In the notes, you limit yourself to lambda smaller than 2. Yes. For some reason, is there a physical reason why lambda should be smaller than 2?
Well, so the thing is that I was kind of rushing here at the end, and I wrote down that infinite matrix, and then I sort of rubbed it out. But the point is that there's another thing here. There's a K1J, and this goes like J to the power nu. If nu is larger than 1, there's something even more bizarre happening that one gets instantaneous gelation. It's kind of a mathematical pathology. But so one has to be a little bit careful when the aggregation rate gets so rapidly increasing with mass, one can even get gelation happening instantaneously. And that part is not so well understood.
When u is bigger than 1?
So if I have K, what is this? So if I have lambda larger than 1 and nu larger than 1, these two things give me instant gelation. So you wait infinitesimal time and you have an infinite cluster. And it's really pathological because it doesn't correspond to any physical system, but it's an interesting mathematical game just to investigate that asymptotics. Chris,
yeah. What if you're in like a mixed regime where one says that you'll gel and the other says you won't?
What do you mean by mixed?
Okay, so like nu greater than 1, lambda less than 2.
That's probably not so well understood. You can start worrying about pathological kernels, and in fact, for problems involving gravitational settling, the kernels that describe that, when you sort of from first principles write down what the kernel ought to be, you end up with things like that, like nu bigger than 1 and lambda less than 1, and it seems like it should blow up, and no one really knows what's going on. Yeah.
So you replace the unrestricted sum by 1 minus k when gelation occurs, and so but then it will be positive for the rate. Ck dot would be equal to plus g times ck.
No. Again, the only place that this correction appears is going to be in the loss term. So let me just write this down. So I have ck dot is equal to summation ij over 2 ci cj. But this is a restricted sum. I plus j is equal to k. And so there's no issue of gelation affecting this gain term because I'm looking at the gain of clusters of a finite mass, and they can only involve clusters which are smaller. The only place it appears is in the loss term, which is which I had here, k ck. sum ICI. And so the only place that gelation can have any role is if here I'm losing a cluster of mass K because it can interact with a cluster of any mass. If it interacts with finite mass clusters, that'll be the sum up to from 1 to infinity minus, but there's also the contribution because it interacts with an infinite cluster. So this thing is 1 minus G. So that's the only place this appears.
So that's why G will be positive, right? Because minus K, CK times minus G, so it becomes a gain term.
No, because it's, I mean, this is describing the loss of clusters of mass K interacting with anybody else. So you want to say there's a minus and a minus that makes a plus term, right? But the thing is that this is still describing the loss of clusters of mass K, because this is CK dot. And so this tells me clusters of mass K are somehow being killed off because they're interacting with, this is...
The way to say it is that G is always
Always
1 or
less.
less.
Pardon me?
G is always 1 or less.
Exactly so.
It's a loss.
That's right. This whole term, this whole thing here is bigger than equal to 0.
Yeah, so when there's more, when dilation fraction increases, the loss essentially decreases.
That's right, because then you're interacting more with the gel and less with the solid phase.
But why isn't there a loss to the infinite cluster? That's what. Why isn't it 1? What?
Why isn't it 1?
It's saying that you're losing K clusters only to the finite clusters, but not to the infinite one.
Well, I mean, excuse me. The thing is that if you think about an infinite system, there is one gel cluster, and
But the one gel cluster can still grow, right?
yes, absolutely.
And that says it does.
I'm going to have to take your question under advisement. I don't have a good answer. I have to think about
Okay,
that.
can we take maybe one last question and then you want to do that?
I didn't understand the physical here, but I have a question. Is the result dependent on the initial condition?
Okay. So let me just say a general statement, which is that everywhere I chose here a monodispersed initial condition for mathematical convenience. If the initial condition is a bounded support, everything still holds. No changes. Just like, details get much harder. If you have an unbounded initial cluster mass distribution such that the mean mass or the mean square mass is infinite, then the infinite scale associated with the initial condition plays a role even in the asymptotic behavior. And it turns out to be actually quite messy. But it's not terribly physical. It's like an interesting mathematical issue. If you have like a broad-tailed initial distribution, then memory of that initial broad tail just remains for all time. So that's basically the answer.
All right, well then let's break for lunch and let's